Hello everyone. Today we'll just continue the linear regression, but we'll mainly focus on the error matrix, which is the mean square error. In this session, we'll try to explain the mean square error in detail actually. So by the time I think you all are familiar with the linear regression, so when you have this kind of data, like these are your x components, so this is like x1, this is like x2, and this is your prediction. Okay, and if you do a linear regression, so which will be something like beta 0 plus beta 1 x1 plus beta 2 x2 and the epsilon, which is the error. Graphically, I think by the time you all are kind of little bit of familiar, like if we do a linear regression, and if we have the points something like this, and if you probably draw a linear regression function, whatever this distance are, this is called residuals, right? The distance between your actual point, so basically your actual point and your predicted point, this distance, the difference between these two, so not the distance, the difference between these two is your error or residuals. Okay, so how do you calculate the MSC? MSC is the error matrix, and this is your loss function also. So MSC, you can say it's a error matrix, or you can say this is your loss function also. And one of the main objective of linear regression problem is to minimize this error actually. And how we can minimize this? We minimize it by taking the derivatives. Okay. Now the question is how we are calculating this MSC and why. So MSC, the formula is summation of y I equal to y I equal to 1 to n 1 by n mean square error. Okay, so basically actual y value of each observation minus the predicted value and whole square. Now the question is why we are doing this square. Why not we are sticking to the mean absolute value? Okay. So the thing is, let's take a couple of examples. So first one is the model one. So this is my model one where I have these actual values, which was 100, 130, 140, 90, 170. And the model gave me the prediction like 90, 140, 120, 100, and 150. So if we just consider the error and residuals, then it's coming 10, minus 20, 20, minus 20, and 20. First of all, if you just do the sum of this thing, what will happen? You will not get the right answer because it will do that plus sign and minus sign, and lot of these things will be discarded, and you will finally probably get 40 minus 10, so which is kind of 30. So when you are doing the square, first of all, you are eliminating this negative signs, right? So that's one advantage. That's advantage one. And then basically you are calculating the mean square error. Okay. So this is the advantage number one. Like, okay, when I'm squaring it, I will basically ignoring this negative values, and error is the error, right? If it is a positive error or negative error, it doesn't matter. I'm just considering the error value. Model 2, let's consider another model which we have 100, 130, same actual values, predicted values are 100, 90, 140, 90, and 200. So in this case, you'll see like just by seeing it probably seems like, okay, I have three almost correct values, but two are wrong values. But these two wrong values are actually very big. So when we'll do the just sum, what will happen? Here you will get the 10. But here, if you do the sum, so you will get, so if you don't do the mean absolute, if you do the mean absolute error, then in this scenario, you will get the total actually 30. You will get total 30, but here you will get 10. So ideally, you might think, okay, this is my better model, but which is not, because we don't want for the few observations where the error is too big. So what we are doing, we are squaring it, and because of that, when we are calculating the mean square error, it's coming 500. So that's mean what is happening in a model, if some of the observations are really poor predictions, then we are capturing that. So basically, by squaring the error, we are penalizing the models such a way that if it has some predictions which are really wrong or large difference, then we are capturing that information. And we can say just by mean square error point of view that this is the better model, because this value is less than this. So this is the better model. Though it has almost all the five has little bit of difference, but still this is the better model. But in this case, you probably has some big problem. Okay. So this is the two things we talk about, the mean square error. Another thing is why we are squaring it, because if you just instead of a square, if you do the to the power 4 or to the power 6 to the power 8, why not? The reason behind is when you do the first order derivative, the first order derivative, derivative, then you will get global minima. So basically, your car will be something like this, and your global minima and your local minima will be same. Global minima equal to the local minima. That's the reason of doing the square. Okay. Now, if you don't do the square, if you do the power of 4 or 8 or something like that, then your graph will be something like it can be anything. Okay, so you will have multiple minima point, and these are your local minima point, and this will be your global minima point. So it will be difficult to find the actual global minima point, because our target is to find this global minima point. That's the reason we are not doing the power of this thing. We are sticking to the square of this value. And this is the most popular error matrix or loss function. And remember it, as part of linear regression, we are trying to minimize these things, and the model which has the less mean square value is always a better model. And now I hope it's clear why we are using mean square error, and hope this explanation you like it, you understand it. If you do not understand, please email me. I'll try to explain. If you like it, please give a thumbs up or subscribe my channel. Thank you. Have a nice day, and we'll talk in the next video.